Squares, what do you know about them? Rectangles, what do you know about them? What you got for me?
It's a square, so all of the corners are going to be 90 degrees.
Yeah, buddy. So we get this.
Whoa. Yeah.
And won't that be the same with the rectangles?
True.
Oh, yeah.
These are all 90. And it's a square, which means what?
I don't know.
All the sides are equal.
Oh, yeah.
So I'll do that by making this x and making this x. Right? That works. I don't know. Something like that. And then the rectangle, we know some sides are congruent. Right? So I think this side right here would be congruent to this side right here. It's the rectangle, right? And then these sides would be congruent. It's a rectangle. So there's that. So we want to figure out the area of this rectangle. What's the area of a rectangle? How do we figure that out? Yeah. Length times width. Yep. There's lots of ways to find a rectangle, but that's probably the easiest one. So length times width. So we need to know this value times this value. Now eventually we'll give those variables, right? And we'll times those together and say that's the length related to whatever the square is. We got to figure out how these relate to the sides of the square. But right now, let's just get things congruent or similar. What do you see? What do you see about this problem? Forget about the area. What do you see? Hannah? There are triangles. Very good. And not just any triangles, but a lot of right triangles. Which means all of our theorems for congruency are on the table, like hypotenuse, leg. And then for similarity, a lot of these triangles already have one angle in common, right? They have the right angle. That's true. So you got a lot going on. What do you see? A parallelogram? We don't know about that yet. Yeah, there is, right here. That's true, yeah.
These two small triangles, maybe have the hypotenuse
Yep, hypotenuse leg, right?
Yeah.
These two triangles are congruent by HL. Here's what I'm going to do. I'm going to take out my pen. I'm going to do a little congruency symbol inside of these. So I know that they're congruent. And we know that by HL, right? Hypotenuse and leg. Nice job, Bailey. So those are congruent. Looks like these guys would be congruent, right? Is there a way to prove that? That's the question. I mean, they have one matching leg. What else you got? Yeah.
The same thing with the two big ones.
Two big ones. So this one right here and this one right here. Yeah, we've got hypotenuse leg, right? We have the hypotenuse of this guy, right? And we have its leg. We have a hypotenuse of this guy and its leg. So these two big triangles would be congruent. So that's good. I'm going to do congruency symbol like this so it goes through everything. So you can see we're talking about those two big triangles. That's cool. So really, if we figure out what these two triangles are, right, then we know these ones for free. And we can subtract that from the square, and then we get the area of this guy, right? So that's another way to get the area of a rectangle, right? Or at least this rectangle, subtract away the pieces of the square. Only we can figure out what those are. Now, again, we're not going to get a number for these areas, right? We don't know how long these sides are. They're in terms of x. So it'll be something like, the area of this one is half x times 3, and this one's half x times 3, and that one's quarter x times 4, and this is the quarter x times 4. And so when you subtract those away from x squared, what's left over will be the area. What else do you see? Well, okay. If this whole thing's x, how much is this piece right here?
1/3.
1/3 of x, right? Let's use a different color. All these are 1/3 of x, right? Cool. Do you know how much this is? No, it looks like it's 1/3, right? And this is 2/3, but do we know that for sure? Not yet, at least. If we could figure that out, we could get the area of these triangles, right? We could do base times height divided by 2, right? So we could figure out these portions right here, we win. Question is, what are they? How do we figure it out? If we can prove that's 2/3 and 1/3, we've got 2/3 x and 1/3 x.
Oh, the sides are equal.
These sides? Is that what you're talking about? Or what sides?
No, the bottom and the side.
Right here?
Yeah,
So these 2 bits are equal?
the long ones.
The long ones. So this and this are equal. What are you talking about?
Yeah,
These 2 sides.
yeah.
Yep, so that's
So
x and that's x, that's good. But we don't know that's a third, right? It could be like a fifth and this is 4/5 or something. You see what I'm saying?
Yeah.
Now, it's gonna end up being a third. The question is, how do we know that for sure? Yeah.
The top angle that's hitting the 1/3 mark.
This?
No,
This.
on the rectangle.
On the rectangle, the top angle that's hitting the 1/3 mark. This?
No, up here. This one.
Okay, this one right here. Got it. Okay.
It's corresponding to the one that's below, like also hitting the 1/3 mark. Yeah. So then, those are the same, but like they're kind of flipped.
Corresponding because they look like they go together. But you mean like corresponding angles?
Like I don't know, like they're in the same position, but they're the opposite angles, so it's.
You're right, there is something with that, but we can't use corresponding angles here because we don't have a transversal and 2 parallels, right? If we could prove these are both parallel, then we'd have this angle here, and we could say something about this angle and, what was it anyway? 2 parallels, 1 transversal, we could say something about this angle and then this angle. Something like that. Like this angle here, is what I'm trying to say, and this angle here. But not quite. Do you see any parallel lines in this diagram? There are a lot, right? Notice these 2 right here. Wouldn't this be a transversal then? Right? 2 parallel lines, there's the transversal. And so we know that if we have 2 parallel lines and a transversal, alternate interior angles, right? These 2 angles should be equal, and these 2 angles should be equal. Now, I bet you're thinking, well, that's 90. That's gotta be. How do we know that? What? This right here? It looks like a rectangle. How can we prove it's a rectangle? How do we know it's not like at an angle or something? Parallelogram.
Because those 2 sides are.
Because these 2 sides.
No, the top and the bottom.
Top and bottom, what about it? Okay, I see what you're saying. So you're saying it's a rectangle because these 2 sides are the same, and these 2 sides are the same.
Yeah.
Right? Which makes it a rectangle. I have a counter argument for you. One, 2, 3, 4 squares, right? 1, 2, 3, 4 squares. And then by p-fag, I know this is the same as this because that's 3 squared, 2 squared rooted, 3 squared plus 2 squared rooted. So is this a rectangle? So it's not enough to just say the side of the figure, right? We also need to know if they're 90 degrees. How can we figure this out? I'm gonna leave this for you guys, okay? We'll work on it the rest of the week. Figure it out early, I'll give you something else. All right.
Ready for the test? Tomorrow.
Why wouldn't we?
There's
like a
6
snow
to,
cake.
yeah, 6 to 12 inches of snow.
I hope we do. And I hope you do.
Snow.
Guys, after this week, it's March. So we have March, April, May. And then you're gone. I'll never see you.
Chevy's birthday.
I will never see you.
I might cry.
I will.
Chevy, I will cry.
I'm not gonna cry. I hate geometry. I'm not either. I hate geometry. I say we all just join game.
I tried it, but it didn't sound like enough.
Can we make the freshmen like not
Before you're
allowed?
running.
Yeah, the freshmen, incoming freshmen are not
Okay.
allowed to
They're
join game
so
club.
yeah, it's from
These
2013.
big guys are for me. They are single-sided
No, I didn't think you were saying.
so that I can write all over them and not have to worry about bleeding through.
This is so
You guys get double
These are
sided.
his two favorite people.
These are for you.
It's his two favorite people to work on. You're right.
We
So
have
sorry.
Why?
No, it's a joke. Like if we bring hats,
Party hats.
Yeah.
I'll bring the hats. You bring the
Wait,
cake.
is it March yet?
You guys have the same
No,
birthday.
it's
so
in-
we're
no,
all
it's in the
the
same month.
person.
It's in the same month.
I know.
8
No,
days
that's
apart.
the only
9.
one.
Taylor, it's 9.
Counting is hard.
Happy birthday is March
Days
26th.
apart.
You. All right, this is part 1 of the Siva Theorem worksheet.
This looks awful.
What?
Sabian's proof worksheet.
I-
Sorry, that's what I
Mr.
call it.
Mac, when was your birthday? I forgot.
When was it?
Yeah.
A long time
The
ago.
only thing I can't remember is birthday.
All right.
Oh.
So,
Does anyone need this? Me.
before we can get into Siva's theorem and a bunch of other theorems and prove things that we took for granted last week, we have to deal with this thing right here. So last week what we did is we talked about all different parts of the triangle, right? The special sections, like the angle bisectors, the perpendicular bisectors, the medians, right, and the orthogonals. And we said that they're all going to intersect at a point. Now we proved that, quote unquote, by going on GeoGebra, moving the triangle around and showing that, look, they all intersect at one point. They're concurrent, right? And we took that for granted, and then we said if that's true, then we have a center, right? We call it an incenter or a circumcenter or orthocenter or perhaps a medicenter, right? We talked about these things. And we said that the medicenter, orthocenter, and all those centers always exist because those lines will always be concurrent no matter what triangle you deal with. And we assumed, kind of like a postulate, that of course they'll always be the same. We can move stuff around in GeoGebra and show that, right? But we never proved it. Turns out you can. So we're going to prove that those centers always do occur, meaning that those lines, if you draw 3 angle bisectors, they will all intersect at one point, right? We talked about how having 3 random lines all intersecting at one point is really rare, right? In order to pull this off and be concurrent, right? I just screwed it up, right? In order to make it concurrent like that, it's very rare, right? To have 2 lines intersect, that's no big deal. These 2 lines intersect, right? These 2 lines would eventually intersect, but to have all 3 hit at one point is pretty rare. So to say that the angle bisectors, I'm getting one out of, the angle bisectors of a triangle all intersect at a point, right? We can't just take that for granted. We have to be able to prove that. Because it is, in fact, pretty rare for that to occur. Where did I put all my extras? Sorry, Oh, you do? Oh, I thought you were looking for one. Are you looking for one? No, you're just passing the stapler around. All right.
Pass the state.
That's right. Okay, so before we can do that and start proving that all these line segments are concurrent, we need to do a couple things first. Now, when we prove things that aren't really about the proof we're interested in, we call that proof a lemma, L-E-M-A. So a lemma is like, hey, just before we get into this, you need to understand this. That way when I use this later, you'll know that I'm not making this crap up. So this is a really bizarre looking thing. It says that we have 3 things in ratio, right? Imagine like our similar triangles, right? We have the sides in ratio. We've been doing that, right? Like we use big letters like AB over CD, right? All that crap. I just replace them with little letters, okay? Now, if this is true, this should be true. And this is really bizarre looking, right? We have A minus C over B minus D equals E over F. And that's not necessarily obvious. And so I want to show you that this is true before we end up using this in a proof later on. This will be true. So what we're going to do is we're going to prove this. So A over B equals C over D equals E over F. That we can assume, right? That's given to us. So we have a bunch of numbers that are related, and they're all equal. They're proportional. And then we're going to get this somehow out of that. Now, before we get into this, let's think about what this means, right? These are 3 fractions, right? And we know that they're all equivalent. So let's make up some numbers real quick, just so we can get an idea of what's going on here. Give me a number for A.
6.
6, awesome. So this is like saying 6 over, give me a number for B.
3.
3 equals, so we said 6 for A and 3 for B. Now C and D could be the same number, but this would be really boring, right? 6 over 3 equals 6 over 3 equals 6 over 3, sure, whatever. Let's make it more interesting. Give me another number for C.
8.
Now, if you want to make this easy on us, because they have to be equivalent,
12. 8 over 4.
12 and what?
6.
6. They relate by 2, right? That's their relationship. They're proportional. Why? Because they both relate by 2. 6 relates to 3 and 12 relates to 6 by the same way. Double. And then the last one, give me another one that relates to 6.
8.
You could do 8 and
4.
4.
Could you do 2 and 1?
You do 2 and 1. Anything that relates by double is true, right? So in other words, these are all equivalent fractions. That's all this is saying. If you've got 3 equivalent fractions, and they can even be written when they're not fully reduced, right? Then you should be able to take those equivalent fractions, those numbers that you used, and mess around with this. So what we're saying is this should be true. So we said A was 6, B is 3, C is 12, D is 6, right? E is 8, and F is 4. Right? That's what we chose randomly. Now, if it's true for any set of numbers, which is what this is saying, right? Then it should be true for a specific set. Right? These are all equivalent, right? 2 over 1, 2 over 1, 2 over 1. So let's try it. 6 minus 12 over 3 minus 6 equals 8 over 4. Is this true?
Yes.
Well, we get negative 6 over negative 3 equals 8 over 4. And when we reduce these both, well, 8 over 4 is just 2 over 1. And negative 6 divided by 3 is also 2 over 1, or 2, right? So it does check out. And this will work for any set of equivalent fractions. So this isn't something you're going to use a whole lot in algebra, right? It's not like, oh yeah, remember that equivalent fractions you can do this with, right? It's not really something we use a whole lot, but it is a true fact. Now, this is a pretty meaningless fact. You can also add them, and it's not very interesting, but it becomes interesting because we're going to use it later on. It's a lemma for a proof we're going to use, okay? So let's prove that this works for any set of numbers. And the way we're going to do that is this. So I want something like this out of that. Now, I'm going to mess with this side to kind of give me a hint of what I need to do over here. So I'm going to take this. This is not part of my proof for my lemma. I'm just going to mess with it a little bit. Now, if I wanted to get A and C on their own, I'd have to get rid of this division, right? How do I undo division? Multiplication, right? I'm not trying to move the D or the B. What I'm trying to do is I'm trying to undo division. So when I do that, I multiply, right? I'm going to separate the A minus C from the B minus D. So the A minus C stays, and then I multiply by B minus D. Now, because there's 2 terms there, we have to wrap that in parentheses when we do that. And so what we get is this. B minus D in parentheses times E over F. Another way to write that is this. I'm going to distribute the E. Remember, multiplication on top, division on the bottom. So E times B is EB minus E times D, which is ED, no jokes, all over F. Just another way to look at it, right? So what I'm going to want is I'm going to find out what A and C are, right? I'm going to mess around with A and C up here, find out what they equal. And then I'm going to subtract them from each other, and what should naturally occur is this. Does that make sense? That's going to be what I do, because once I get here, then I just work backwards, and I win. I get the thing I wanted, right? So this is going to be my goal. I'm going to get A and C, figure out what they are individually, then I'm going to subtract them, and I'm going to get something like this and mess around with math, okay? It's kind of like when we did PFAG, right? My goal was I wanted to get certain letters on their own, like A squared and B squared, right? Figure out what they equal. And then I can set up A squared plus B squared, see what they equal, and then mess around with stuff, right? So that's what I'm going to do. So let's mess around with this. So A over B and C over D. Because I want to get A and C on their own. Okay? So squiggles. I want to get A and C on their own. So A over B equals C over D, and it equals E over F. I'm going to set it equal to E over F here again. I'm just going to ignore the C over D, because I want to figure out what A is and C is. So I don't want a C over here, and I don't want an A over there. So I'm just going to say this, which is true, like that was given to us. And then what I'm going to do is I'm going to get A on its own. How do I get A on its own?
Times B.
Times B. So I get A equals EB over f, right? I multiplied by b, multiplication goes in the top, division goes in the bottom, right? And then same thing for here. Isn't this ED? No jokes. So now I know what A and B are. Or A and C. Right? Cool. Now I think you might see where I'm going with this. A minus C should be this minus this, right? And that's going to give me this. A minus C should be this minus this, right? So if I do that, I'm going to say, look, I can take A and subtract C anytime I want. I can't tell you what it equals, just I can't be like, hey, it equals 5 or it equals Z or something, right? I can't do that. But I can tell you that, well, if A is EB over F, right, if I substitute, I get EB over F minus substitute ED over F. You cool with that? You follow my logic on this? Just substitute. That's what A is, that's what C is, right? So they should be equal. And then I'm going to say that A minus C, since these all have a common denominator of F, can I put them all over F? Right? If that was 2 over 3 minus 4 over 3, couldn't I put them all over 3? Right? So I'm going to put them all over F. And if you look, now I'm here. Right? So if I go from here backwards, I'll get what I wanted to prove. This was not part of my proof. It was just me figuring out, look, this is an easier spot to get to, and if I get there, I win, right? So I got here. So now what am I going to do to get what I want? What am I going to do to this? You can cheat. It's just the reverse. What am I going to do? What do I do to get from here to here, working backwards? Well, originally I distributed the E, right? So we're going to pull out the E. It's a valid strategy. So we pull out the E. We get B minus D over F. Now check to make sure we didn't break algebra. If I were to go this way and redistribute that, if I were to undo what I just did, would I get back to what I did? E times B minus E times D. Yeah, I would get back what I got. So I didn't change any math. I just made it look different. And I can write that like this. Right, it's all multiplication. E times the quantity of E minus D all over F, or E over F times B minus D, right? It's all multiplication. It's fine. This thing times that thing divided by that thing. This thing times that thing divided by that thing. They're both the same. Now what do I do to get from here to what they wanted me to prove? What do I do? From here to what I wanted to prove. Divide by the quantity of B minus D, right? Remember, we don't say parentheses B minus D parentheses, right? Parentheses is hard to say. I can barely say it. We say the quantity of B minus D, okay? So I'm going to move that over by division, and I get this. Done. Okay? So I started with what they gave me. I found out what A and C were. I set them up, and I knocked them down. How did I know I wanted to get A and C on its own? Because I knew this really right here, if I can get to this, I can get to this, right? Just working backwards. Cool.
Can you scroll down a bit?
Yep. So do you believe me now that it works for every number? I think we've seen it with numbers that it works, right? And this shows that it works with any numbers. Okay. A, B, C, D, E, F. You cool with that? So I don't want you to be shocked when you see that later. But you will be. Ready? Here we go. All right. The area of a triangle is proportional to its base and its height. Okay? Proportionality, right? Division. Means how they're related. So the area of a triangle, that's what that means, equals base times height divided by 2. Do you agree? Cool with that? Okay. So check it out. Another way to write that is to say that the area of a triangle times 2 divided by its height equals its base. How'd I get there? How'd I get that? That's bizarre looking. How'd I come up with that?
Times 2.
I times 2, I moved 2 over, right, by multiplication.
And then divided h.
And divided by h, right? I solved for b. Now couldn't I do the same thing with this? Right, times 2 divided by b, get h on its own. So the area is proportional to its height, right? They're related. See how the area is related to the height? And the area is also related to, related to its base, right? And how they are related is this. So, we said earlier, 6 and 3 relate the same way that 12 and 6, the same way that 8 and 4 do. And what's the relationship?
2.
Double, right? So if you take 6 over 3, we say they're proportional. How are they proportional? By double, right? This tells you how they're related. The answer, right? 6 divided by 3 is 2. That tells you the relationship. That's why we write proportions as division, because it shows the relationship between two numbers. 6 and 3, how do they relate? By 2, right? Area and height, how do they relate? By the base. Now you might say, well, that's double the area. Okay, you don't like the 2 there? Here, I'll put the 2 here. How do area and height relate? By their base divided by 2. That's just some number, right? That's the relationship. If you took the area divided by the height, you get base divided by 2. And that would be their relationship, whatever that number is. Cool. So the area of a triangle is proportional to its base. So we can write that like this. Area of a triangle is proportional to its base. Or you can do the height, right? We're going to talk about the base today. This is always true. How does it relate? Well, we know it relates by this, right? Height over 2. We're not going to bother with that. All we're going to say is, look, it relates. Okay? Area of a triangle is related to its base. All right, so check it out. How many triangles do you see?
3.
3. 1, 2, and 3. We have 2 triangles that are inside another triangle, right? Now, are they similar? I don't know. I can't prove that. You can imagine that they might not be, right? This could be equilateral, and this could definitely not be equilateral, and they wouldn't be similar, right? Equilateral triangles have 60-degree angles, right? And this would have not 60 degrees for every angle, so they wouldn't be similar, right? So we can't really say anything about these triangles, right? We can't prove any similar to each other. There's nothing. But what we can say is that the area of some of the triangles are proportional to a base. So check it out. This triangle is going to relate to its base, right? The area of this triangle will relate to its own base, right? How will it relate? Well, height divided by 2. Sure, some number. And this triangle has its own base, and they'll relate, right? Now, something is very interesting about these 2 triangles. They have different bases. But what about their heights? They're the same. They're the same height, right? From here to here is the height of this guy. And isn't it that same line the height of this one? They're the same height. Now it looks weird because one's at an angle. But because they're both inside this triangle, these little guys have the same height. Right? It's interesting. The area of triangle ACD is proportional to its base. AD, right? And the area of triangle BCD is proportional to its base, right? BD. We know this to be true, right? That's nothing crazy. This triangle's area should be related to its base. This triangle's area should be related to its base. We know that, right? That's always true. What's interesting is this. What is the area of triangle ACD equal to? Well, it's half its base, right? What's its base? We'll call it C, little c, right? times its height. What's its height? What do we call it? What do we call the height? H. Okay. Okay. Interesting.
Why'd you say half C?
Half little c. Half base times height, right?
Oh.
Base times height. Area of this triangle, BCD, what is it equal to? Half what? Little d times h. So they have the same height. Interesting. Check it out. If I take the area of this triangle, ACD, and I divide it, and I relate it to the area of this triangle, what's that going to equal? These two being divided. Use substitution. What will this equal? We use substitution. Don't be afraid to answer. What's this top part going to be? Yep, go ahead, Shelby.
A.
The top part right here?
Yeah, I don't know.
What's that all going to be? 1/2 c times h. And what's the bottom going to be? Half dh, right? Now, what do you notice about this fraction? What's h divided by h? 1, right? So that becomes 1. And what's half divided by half? 1. Right? Anything divided by itself is 1. So we have 1 times c times 1 divided by d. What's 1 times c times 1? C over d. So I think we've just shown when two triangles have the same height, right? That's why those heights cancel, because they're the same, right? When two triangles have the same height, their bases are related. They're proportional. So if two triangles have the same height, their bases will be proportional to their area, right? So we can say that area of this triangle over area of the other triangle is proportional to their bases. Meaning that if this area is twice as big as this area, this side, this base, will be twice as big as this side, right? So if I know this area is 12 and this area is 6, they're related by double, right? That means if this base was 3, this would have to be 6, right? So if these are double, then these are double. This only works when the heights are the same, right? Because when the heights are the same, they go away when we set up the proportion. If they're not the same, then they don't go away, and we get CH over CD not very interesting, right? So when the height's the same, the bases will relate the same way the areas do. That's all I'm saying. Is everybody cool with that idea? Right? If that's 3 times as big as this guy, then that segment is 3 times as big as this guy. Only true for the bases when the height's the same. Those are our two lemmas. The areas, if they are proportional, then the bases will be proportional. Okay? When the height is the same. And then the other one was that weird proportionality thing, right? We got A minus C over B minus D equals EF, right? New definition, a Cevian. We've talked about Cevians before, we just haven't called them that. So a Cevian is any segment that connects a vertex of a triangle to its opposite side. And that includes when we extend that side. So for instance, this is a Cevian. because it goes from vertex to opposite side, right? This would also be a CBN. I'm going to extend this side out. That would also be a CBN. So CBNs can go outside the triangle. It's anything that goes from a vertex and it connects with the opposite side. Is that cool? Now, we've talked about CBNs. CBNs is just a general term for anything that goes from vertex to something on the opposite side, right? What special segment did we learn about last week that goes from vertex to something? Vertex to midpoint, which one is that? A median. So a median is vertex to midpoint, right? Here's vertex to midpoint, right? Is that a CBN? Of course, it goes from vertex to the opposite side. Now this is a specific type of CBN where it goes to the vertex to the opposite side at the midpoint, right? But it's still a CBN. What about from vertex to 90 degrees to the opposite side? What about something like this? Orthogonal. That's a special type of CBN. Right? It's a CBN where it goes to the opposite side at 90 degrees. Another one. What kind of line segment is that I just drew? It's not just an orthogonal. It's not just a median. It's kind of a combination of the two. What is that? Nope.
Perpendicular.
Perpendicular bisector. Very good. And then Taylor, what kind of line segment is that? Angle bisector. Those are all CBNs, right? They're just special kinds. This CBN right here, we don't know whether it bisects the side, we don't know what angle it hits at, we don't know if it cuts these angles in half, it's just some kind of line, right? CBN's just basic. And that's okay. You can be basic. These are just more specific kinds of CBNs, right? So what we're going to do is we're going to talk about all CBNs, something that's true for all of them. It doesn't matter if they're special or if they're just basic, okay? And that CBN theorem is called Civa's theorem. That's what CBNs are named after, this person Siva. So it says if CBNs AE, BF, and CD are concurrent. So look, AE, that's a CBN, right? It goes from vertex to the opposite side. BF, that's a CBN. It goes from vertex to opposite side. CD, CBN, it goes from vertex to opposite side. If they're concurrent, which in this diagram they are, right? They all intersect at one point, then this will be true. A over B times C over D times E over F will equal 1. So if all these CBNs are congruent, when you multiply all these together, you're going to get 1. We're going to prove that. Page. All right. We had 2 lemmas we talked about, right? That I said we need for this proof. 1, we talked about the A over B equals C over D equals E over F, and we can rearrange that to be A minus C over B minus C equals E over F, right? The minus thing, right? That we proved first. Then the second lemma that we did was this guy. Or is that the first lemma? Oh, that was the first lemma. Here's the second lemma. Second lemma was we said this. If the heights are the same, then the areas relate to their bases, right? I'm going to use both of those. Come on, paper. What do you notice about the triangle on page 4? We got a bunch of CBNs, right? How does that relate to our lemmas? Look at the first 2 lemmas, especially the one that relates area of the triangles, right? Don't we have a bunch of triangles that are inside another triangle, right? Look at triangle ACD. Look at triangle BCD. Aren't they two triangles that have the same height? They are, aren't they? Which means what about their bases? They're proportional to their areas, right? So the area of this triangle over the area of this triangle will equal A over B. What about this triangle here? AEB. Isn't it a triangle that's inside the big triangle, right? We have two triangles, AEB and ACE. So their areas will be proportional to their bases, right? And over here, these triangles, their area will be proportional to their bases. And that's going to get us a bunch of equivalency of A over B, C over D, E over F. And we know what we can do with that, right? We can move that around. We did that in our first lemma. So here's what we're going to do. I'm going to say that the area of triangle, let's call it ACD, over the area of triangle BCD equals, well, by our lemma, right, we know that if the area of this one and the area of this one are proportional, they should be proportional to their bases, right? Little a and little b. Cool. Now, I could say that for all my other triangles, but I'm going to save that for later. What other triangles have these bases and share a height? Well, we said the two big ones, right? B, say it again. BGD, AGD, right? These two triangles. You guys see that? So their area should be proportional to AB. So the area of, let's use light blue. You said AGD, triangle AGD, right? And triangle BGD should be proportional. Because their heights are the same, right? So check it out. These two triangles right here, the height of this triangle is the same as the height of that triangle. All right, we'll talk about this tomorrow. Come in and correct / complete your test. Make sure you study up. I will give you one shot to do it. No coming back later.